Convolutional neural networks have revolutionized computer vision, with applications to various tasks such as object detection and identification. Since the first models, it called attention with competitive results. CNNs have become more complex, with a higher number of parameters. These models are considered black boxes, implying that one cannot explain their decisions. Thus, explainable artificial intelligence has appeared to address the problem and avoid wrong interpretation of the results. Besides choosing a suitable architecture and training hyperparameters, the designer might also have to count on an expert of the application domain who must provide a dataset with sufficient number of correctly annotated samples for the model's training. Even though recent studies have focused on the first problem, none of them have considered exploiting both raised points. In this video, I'll talk about an interactive method to estimate the weights of convolutional neural networks without the need for backpropagation. Given the architecture of a CNN, this method called feature learning from image markers is able to estimate the weights of the features of the convolutional layers from markers in images. To evaluate the ability of these methods to produce good feature structures, we apply it to the problem of interactive object delineation. We compared feature structures learned with FLIM with feature structures from a lot more complex CNNs. Our proposal is only to evaluate the quality of the feature structures and not a new approach to the problem of interactive object delineation. The rest of the video is divided as follows. I'll give a visual motivation for the method. Then I will present the dataset used and what experiments were carried out. And finally, present the results obtained. Let's say we have a dataset X and that we have a mechanism phi that turns X into something that has some characteristics that we want. For example, in our classification problem, we want phi of X to have some properties that facilitate the task of discriminate among samples from this dataset. Let's see an example. Let's say you have a problem with two classes, blue points and red points that lie in a 2D space. Here, blue and red points can represent anything, but each sample has two features, which are its coordinates in space. Note that these points are more or less divided in three groups. Note that we are unable to properly separate the group of red points from the groups of blue points using a line. In other words, this problem is not linear separable, but you can do something to turn this problem into a linear separable one. Observe this transformation. We went from a 2D space to a 3D space, and it is now possible to draw a plane that separates the red class from the blue class in an acceptable way. But what transformation was that? Again, we have that two classes are divided into three groups. Note the vectors that points toward the center of these three groups. Observe these planes orthogonal to these vectors. Note that each of these planes somehow separates one class from the others, each group from the others. For the green plane, we need to shift it a bit to find the point at which it best separates those blue points from the rest. To avoid the need to shift the green plane, we can subtract the mean of these points and send them around the origin, and divide by the standard deviation to standardize them. Now look again at the vectors that point to the center of each group. Now, we're going to take the dot product between each of these points and the three vectors. That is, multiply each vector by this matrix. We have a transformation that takes points from 2D space to 3D space. For each point, the three new coordinates are the dot product between the point and each of the three vectors that point to the center of each group. But this transformation alone still doesn't seem to be enough. So, if we zero out the negative values for each point, we will make each group lie into one of the three axes. It is now much easier to draw a plane that separates the red class from the other classes in an acceptable way. This was the transformation that we used to map this nonlinear separable problem to a linear separable one. We built a feature structure. Note the similarities of this transformation with the convolutional operation normally used in convolutional neural networks. We can see the transformation we made as a convolution, in which the three kernels are the vectors that indicate the center of each cluster. We apply this convolution to each point and create a new 3D space in which the dataset has a certain property that we want to be linear separable. Therefore, the method we are proposed to learn features from image markers is based on this idea. Only we have images. Let's take a look at how a method to learn feature structures from image markers works. Let X be a dataset of images. In this context, we don't want to classify images, but classify pixels. Therefore, each image pixel has a label. In an interactive object delineation problem, the label of a pixel says which object that object belongs to. We need to draw markers on these images in regions that we think are relevant to select the object or objects we want to segment. As the task is interactive, the user must place markers in all images. We can see each image as one dataset, so we can create a model specifically for each image. As FLIM can build a feature structure really fast, the user is able to build the model interactively. Let's take a look at the convolutional operation again. We have a kernel sliding through an image, and for each pixel, the convolution operation is the dot product between the kernel's feature vector and the pixel's feature vector, which includes neighbored pixels. If this kernel is good for identifying the object of interest, it must produce positive activation in regions that contain this object. If we take some of those regions and use them as kernels, we can produce kernels that are effective for filtering useful features to identify the object we want to delineate. To do this, we draw markers in regions that we think are important for identifying the object. We take a patch around the marker's pixels. Those patches can overlap. We must do this for the other objects in an image or for the background. And now we have a large number of candidates kernels. Each of these candidates can have several channels, and as we don't want to learn a bias for this convolution, we have to perform a normalization that we call marker-based normalization, in which we learn the dataset's average and standard deviation per channel based on the patches that have been labeled. Then, we centralize and standardize an image using this information. To choose which patches will be the kernels we use for convolution, we cluster these patches and take the centers of the clusters. The dot product between each point in that group and its center must produce positive results for that group and negative results for points of other groups. Then, we can use the group center as kernels for convolution. In this way, the kernels of each group are responsible for identifying features of these groups, and thus we can use them as filters to find these features in the image. The whole process can be summarized in these steps. Start patches from around markers, clusters those patches, and apply the convolutional layer. To apply FLIM to some problem, one can follow these steps. Draw markers in an image, apply FLIM to build a feature structure, use the feature structure, and if the user feels the need to improve the results, they can add more markers. As the user adds markers to enhance the delineation, we can update the model with new features learned from the new markers. To evaluate our method, we applied to the problem of interactive object delineation, in which the user wants to select an object in an image. To do so, they place markers that indicates where the object is. We use the GeoStar dataset. It consists of 151 color images of up to 800 by 600 pixels each, a set of user draw markers per image, and the ground truth segmentation masks. The number of markers and size varies from image to image, but they all are 5 pixels wide. These are some images from the dataset. This is the pipeline we use to delineate objects. We use a feature structure to compute features maps. We get the gradient of those features maps, producing a grayscale image. We give this magnitude gradient image with the user markers to the watershed which delineate the object. Our objective is to compare feature structures, not to propose a delineation solution. For a given set of user draw markers, FLIM may take some seconds in CPU to learn a simple convolutional neural network. Therefore, it should be feasible to develop strategies that optimize the model's architecture in a layer-by-layer fashion. We evaluate the segmentation pipeline for 19 different models per image by varying the number of layers, size of filters, and the number of filters per markers. Here are the hyperparameters we used. Assuming that architectural optimization is feasible, we selected the best model per image in order to compare its results with the other feature structures. We evaluated the following scenarios. The feature structure learned with FLIM using the GeoStar marker set. The feature structure learned with FLIM using our marker set. As baseline, we considered the following scenarios. We don't use a feature structure. The gradients obtained in the lab color space of the input image. The first block of DeepLab v3 as feature structure. Until the last block of DeepLab v3 as feature structure. We use the DeepLab v3 trained on the Pascal dataset. We use the mean intersection over union as metric. Here, we can see the mean, max, median, mean, and the standard deviation of the mean intersection over union for each scenario. On average, DeepLab's results were well below expectation. This may have happened due to the loss of spatial resolution due to the fact that DeepLab has many layers with a stride greater than 1. On the other hand, the results using FLIM feature structure were way above the other options, showing that the feature structures learned with FLIM are effective to capture good features. Let's take a look at some example of segmentation results. On the left, the results of the feature structure learned with FLIM, and on the right, with the first DeepLab's block. Thanks for watching.